I'm Dr. Anderson from Morgan State University. On the line with me is Dr. Ed Dillon. He's professor over in the Department of Computer Science, and Dr. Simone Gibson. She's actually one of my colleagues in the Department of Education, in the School of Education, Department of Teacher Ed. And our project was computational thinking through culture, making computational thinking accessible to diverse student populations. So when we sat together, and we worked on our proposal, we really wanted to kind of think of different ways. Ed, advance the slide, please. We could think of different ways to, how can we get our students engaged in this? We prepared elementary education majors. And when you look at the research of the disparities and underrepresentation in the STEM pipeline, we realized that in order to get that diversity in the STEM pipeline, we have to begin to prepare students earlier in their educational career. And that bodes true for students of color and for females. So we really wanted to kind of look at a program about how could we get these elements of computational thinking embedded into elementary education early on, and really what we had to do to raise the capacity of our pre-service teachers to kind of be familiarized with these skills and how we can help them integrate it into their teaching. So we had two basic goals: one, to enhance the content knowledge for teachers, and two, enhance pedagogy. Understanding just because you know content doesn't necessarily mean that you can actually teach content. The challenge of it is just that how do you raise and increase the content knowledge of teachers when you're limited to 120 credits? And getting elementary education majors to go back and to take additional coursework really is challenging, to say the least. So we really wanted to kind of look at different and creative ways that we could get them this new content without increasing or adversely impacting their program of study. So we took a look at what are some of the courses that we offer in our department where we can begin to embed computational thinking in. And I am a trained math educator. So I teach 2 of the 4 required math courses for elementary education majors. I teach 2 of those courses. So I really saw that as an opportunity where I could embed some of these ideas and these concepts as I delivered instruction in these 2 math courses. And we also identified other courses in the elementary education curricula that we could really embed that information into. So we have there's a methods class. I teach the math methods course, elementary math methods course. I teach the elementary science methods course. And those are some opportunities to kind of embed that information in there as well. So that's kind of the overview of how we approached it. So for the first year of the study of the program, we really spent a lot of time in the math classes. With my method students, I had them log on and create accounts in code.org, and I just had them go around in there and play around with some of the lessons in code.org, and I really had them create enrichment units in their lesson plans about how could you engage your students in this as you provided your math instruction during enrichment time that I have them planned for. But a lot of the computational thinking and a lot of the brain power really went into what they were doing in the 2 math courses that I teach. Simply because I wanted to show that computational thinking wasn't a new concept. It was already embedded in the concepts they're currently learning in class. And we actually had a little fun learning about it. Next slide, please. So one of the things that we looked at is just, we took a look at the guiding questions is, how does exposure to computational thinking within a math course influence candidates' exposure? So once again, is just that when you're training teachers, exposing them to information and then having them comfortable to present information and talk about information are 2 totally different things. So we really wanted to kind of talk to our students saying like, well, once you got exposed to this, how are you actually processing information? And that does exposure, computational thinking influence their exposure and comfortability in acting it in their classrooms with their particular students. So as you guys know, we're fresh in preparation for our CAPE visits. So student reflection is a really, really big piece of the work that we do. So we spend a lot of time, processing with the students about how are they interpreting the information that they're getting. And moreover, once they have this information, how is it influencing the instructional decisions that they're actually making, as they begin in their teaching and things of that nature. So that's what we looked at. Next slide, please. In addition to that, so we're HBCU, so and we have a really strong social justice mission in our department, and we have a dedication of culturally relevant pedagogy that we embed in all of our courses. So one thing that kind of emerged, with this pandemic is the COVID-19 pandemic really exposed inequalities in our public education system. We found out that students, because we have interns that work primarily in Baltimore City and in Baltimore County, and we found out that those students didn't necessarily have access to technology, and our students struggled to get on board with the technology that Baltimore City was using as they kind of needed to complete their hours. So one of the things that I had to do that we had to pivot is that how can we teach computational thinking with limited access to technology? And that's one of the key pieces that we kind of struggle with, is just that there was always an assumption that you always have technology at the school, but what happens when you don't have access to the schoolhouse? So we kind of tweaked it a little bit, where when we talked about computational thinking, we identified existing platforms that are accessible, and seeing how can we teach these particular concepts within either the Microsoft Office suite or the Google G Suite, using the application of Excel or Google Sheets. And I'll explain that a little bit further. Next slide, please. So what I did was I teach two math courses in the thing. I teach Math 107, which is really the number system, the Math 108, geometry and measurement. And if you take a look to the left-hand column, I identified common elements of computational thinking. We had decomposition, pattern recognition, abstraction, and algorithm design. And what I did was I identified concepts that are taught in the math courses, and I aligned them with these computational thinking pieces. So for example, when you decomposition, you break it down. I asked my students a question: where do you see decomposition in the content that you're learning? So here are a few examples in the chart that's provided on the screen. So Math 107, the concept of making 10. So when when you're teaching elementary mathematics, you want to break the numbers down, you always want to make 10. So when 17 can be broken down into, say, 10 plus 7 and so forth and so on. Prime factorization is another one. It's just that if you listen to prime factors of a number, you're going to take a product and you're going to break it down, identifying the prime factors. And just basically number decomposition when we're teaching place value. So a 185 can be broken down as to 100 plus 80 plus 5. So one of the things that I really tried to do with my students is I wanted them to make the connection that computational thinking isn't anything new. It already exists in current topics that you're learning, but I explicitly made those connections in class. Decomposition, is evident in geometry and measurement as well, where you have points, lines, and planes. You have regular polygons versus non-regular polygons, and just exploration with that as well. So, for example, if you have if you're taking the area of a non-regular polygon, you can break it up into two areas of regular polygons that you actually have formulas for. So what I purposely tried to do is I tried to, in the teaching and the delivery of the mathematics, I actually had the students say, okay, well, when you think of computational thinking, what concept of computational thinking can you align this with? And this is what's illustrated here on on the chart. The cool thing of it is that as the students began to make connections, it was really interesting because those connections really helped them deepen their understanding just on the concepts in and of itself. And there was evidence of that in some of the hands-on activities that we were able to do with them during the semester. Next slide, please. So what I did was I was working with this with a number of students. So I had 2 math 107 sections in the fall and the spring, and I had 2 math 108 sections, and that just kind of gives you the number of the component of the participants in there. And essentially what I did was within the classroom, I actually had one of the activities, they were applying the math concepts in a manifestation of computational thinking. And that's where Ed is going to come in. So go on to the next slide, Ed.
Yeah.
Yeah. So this is kind of, so as we plan the workshop, we're planning a virtual workshop, but the workshop activities that we're going to describe here are an extension of classroom-based activities that I actually did in my class. And Ed's going to lead you through that, and I'll kind of chime in as he kind of talks about this.
Okay. So good afternoon. So what's going to happen here with this workshop here? So when we get our participants, they're going to be exposed to 3 major things. One is creating and modeling a computational thinking framework, which will be more of the abstract aspect of it. Then step 2 and step 3 is going to be more of an implementation or concrete aspect of it, where we're going to look at one thing is applying simple applications requiring basic coding concepts using Excel. And then eventually we're going to segue them from a higher level approach of that to a more low level coding approach using an actual Python, a programming language, for example, using Python. So to kind of break it down from step 1 through 3, so going back to step 1, so how the framework is going to work is, so first we're going to have the participants be exposed to what's called conceptualization. So they be exposed to a different set of problems. So during the process of the problems, they're going to have to be able to conceptualize or even discern the type of things they will actually need in order to actually scope out the actual items for the solution that's required for that actual problem. So case in point, so me being a computer scientist, and I do this in my computer science courses, so I have my students, like, they'll read a problem. And then from that problem, they have to discern whether they need, like, is there an if statement or else statement required, or some type of for loop or while loop or some type of function, or some other type of paradigms or concepts that are actually needed in order to solve the problem. So that they flesh out the different items that are actually needed to solve this problem, the next step is next will be pseudocode, where they have to flesh out the different sequence of actions with those respective items in what order they should actually occur and how they should be executed respectively. And like in many cases, they'll write this out in just plain text, what this should look like. So once they complete that part of the actual pseudocode, that should be kind of like their legend going to the actual implementation phase. So like I said, for step 2, it's gonna be more of a higher level approach, where in this case, using things like, like the system like Excel, a lot of this, the actual concepts and syntax is more embedded and scaffolded, where they be focused more on using like drag and drop and point and click to solve problems, especially for like, arithmetic and geometric calculators, or even things around using programming cells in that regard. But
hey,
finally,
before you go on, in a way that manifested in my class, so in geometry, when we do measurement, suppose they actually had to calculate, say, the perimeter of a rectangle. So of course, in order to find a perimeter, you actually have to add the length of the different sides. So I had my students create a little activity in Excel where they would be able to put in the lengths of the different sides and have Excel would actually tell you what the actual perimeter of it is. So if we had a triangle, side A is one measure, side B is another measure, side C is another measure, and then the perimeter is the sum of A, B, and C. I had my students go into Excel and program that cell to add up the amounts from the 3 previous cells. So one of the things is that, so from a math instructional perspective, they're finding new and innovative ways to teach the concept of perimeter, where they can actually, in order to find a perimeter, in order to program the perimeter, you would actually have to know the formula in order to do that. And then the formula is, because they're college students, you know, the gambit and complexity of the formulas that they will program will really expand a lot more in Excel, or really having them just have different opportunities of saying, identifying a question, what is it that you want to solve? And how can I create this tool to help me with it? But you need to be explicit on what it actually is going to do. So go ahead, Ed. I'm sorry, I didn't mean to cut you off.
No, you're good, man. You're good.
Mm-hmm.
Yeah, so the third part is going to be more of a lower level aspect, as I said before. So rather than using like a higher approach using Excel, we're going to actually expose them like even like computer science more ish type of programming interaction, right? Where we actually use more syntax based text to actually have them flesh out the implementation of their pseudocode to solve a solution. And we can do this using, so there are free, like I said, since like at Morgan State, there is an issue in regard like for us having accessibility type stuff. So no, like for example, Idle is like free where you can download. Also Replit is actually a web-based actual editor you can use directly on the internet to actually build Python solutions. So we actually have our actual participants use this as well. So it's kind of like I said before, we go from the abstract part of step 1 to a high level implementation to step 2, then our low level implementation to step 3. And that concludes our presentation. Chris, Simone, you have any other things to add to this?
Well, this
no.
is Simone. I'm a reading person. I just wanted to take a second, and I say I'm a reading person because this is all super new for me. So my role within this is to, one, learn, but two, to make sure that this is user-friendly reading terms for our candidates, because y'all hear Chris and Ed and most of the folks on this call, y'all are so steeped within this world. So I was fortunate enough to be brought in. Chris brought me in so that, again, someone who's not as familiar with this can make sure that we are presented in ways that makes it super user friendly. So Diane and the folks at MCCE, I'm really grateful to you all for giving us funding to come together. Y'all know typically we work within our own silos, but through this grant, we've had the opportunity, Chris and I, to collaborate. He's a math person, I'm a reading person, and then also for us to connect with Ed, who is super brilliant. So thank you so much for giving us the funding and the opportunity.